I am Allison Schwartz. I'm head of Global Government Relations and Public Affairs for D-Wave. We are excited to have the panel of experts here to talk about breaking the frontiers of applied quantum. You heard from previous speakers about moving into production and commercialization and some of the really cool applications are coming here. So with that, I have Rima Oueid from Department of Energy. She'll talk a little bit about some of the work that's being done at Department of Energy on the applied side. I have Dana Linnet from Artificial Brain. They are a startup company that is working with a variety of different vendors on applications both in energy, emergency response, and I'll let her get into that, and Andrew King. He works at D-Wave and doing some really interesting work, which he'll talk about in kind of breaking the grounds of quantum and AI and other things. So with that, thank you guys for being here. I'll take a seat. So we have kind of the hardware, the software, the government sitting here. And I want to kind of start from the government side, Rima, if that's okay. DOE has invested a lot of time and focus on hardware, but you're doing something different with your quantum sandbox. Can you talk a little bit about that and why?
Absolutely. We saw a great need for looking at the use cases and the applications and learning how to tinker with the actual energy infrastructure. So a lot of the work that's being done out there, is especially within DOE that was done, was to stand up these QIS centers to really do the basic science research. But what we're doing with the sandbox is saying, okay, what's good enough and what can we do with what we have? And we're realizing that in the energy sector, we have use cases that might actually make sense for quantum annealing and for NISQ computers. So optimization is some potential opportunities for us, and that's where I think annealing will really shine. And then in terms of NISQ computers, there's heuristics that we use that to answer some problems that we use to do contingency analysis on the grid. So we don't need a precise answer, we need a probability range. And so we might actually be well positioned to explore that. And so what we really need to do is learn how to build these algorithms. And we do see some opportunities where we can potentially even leverage AI to help us develop these algorithms. But I think, we're not gonna learn unless we start playing and learning by doing.
That's wonderful, and I'm really excited about kind of the breaking grounds in research that your team is working with Oak Ridge on with the GridQ program. And you talked about looking at breaking algorithms and finding those and developing those. So Dana, I'm going to turn it over to you because I know that Artificial Brain has done some work on use cases in the energy space. So could you talk a little bit about that?
Yeah, thank you, and this is great because we can definitely help you. We actually did a lot of work on energy grid and other types of energy use cases. So when you look at the energy market, because we want to approach it both from a government resiliency perspective, but also it has to make sense for the commercial market or it's not going to work. But we look at energy production, producers, distribution across multiple jurisdictions, and like you have a wind farm in Oklahoma, but it spans Texas and Tennessee and all these other places with lots of regulations on it. And then you look at the consumer demand, and when you take the production, the demand, the distribution, and the grid operations, you now all of a sudden have a very complex set of factors you need to, one, protect and make more safe and resilient, and two, optimize from the commercial perspective in terms of the money you spend, maintaining and developing that grid. So we actually developed through our, and just to back up, Artificial Brain is a quantum computing software company, and we make a proprietary, very user-friendly interface platform called Planck, where you could just drop and drag your values in, and we would calculate it. And we use D-Wave's hardware. And actually, 2 summers ago, I think it was, at Qubits, I was part of the CEO, Alan Barrett's keynote, and we demonstrated Planck for energy live, where we optimized for 60,000 different constraints and variables. And we know that AI kind of fails around 8,000 or so. Well, we did 60,000 variables, and we solved it live in front of this audience in 16 milliseconds. So when people say that quantum can't be used and we can't find the software, well, just give me a call, because we can do that. Thanks.
And since Dana didn't say it, Planck is with a Q, if you didn't guess.
No, it's not. It's
Oh, it's not?
Planck after Max Planck. Yes.
CK, I thought it was Q. Oh,
No.
Here I am, I'm wrong.
We're being original, very originalist.
Well, one of the few companies here that doesn't have the Q in it.
Exactly, yeah.
That's a great segue, Andrew, to kind of the work that D-Wave is doing in, there's a lot of this application development. There's a lot of this kind of research. How do we test it out in a sandbox program? But there have been some applications that moved into production. Could you talk a little bit about kind of what's in research and what's kind of moving into production?
Yeah, so D-Wave is another company without a Q in it. And I work very close to the QPU, very much on the research side of it, but we do have research applications and production applications. So just to name a couple of examples, Ford Otosan in Japan has made some great progress with production applications in job shop scheduling, and Pattison Food Group has also done some great things where they've saved 85% of the time that they spend on personnel scheduling. So there are use case applications like that are actually in production being used by our customers. Now, the stuff that's a little bit closer to my work, we've demonstrated beyond classical computation in quantum simulation. So these are the two strengths of quantum annealing right now, is simulation of quantum dynamics, which is basically, to put it very bluntly, intractable for classical computers. And then if you look at the other application is optimization, which is extremely ubiquitous.
That's fantastic, and I appreciate you talking about kind of the work that Ford Otosan is doing in Turkey with automobiles. You had mentioned Japan. It's also NTT Docomo's telecommunications network. But there's been some interesting research that came out of the ERDIC Research Lab. So this is the Army Research Lab that's based out of Biloxi. Could you talk a little bit about that work?
That was basically a network separation problem. So this is a really nice kind of spatially two-dimensional optimization problem where you have to protect certain nodes from other nodes. This is one way of looking at it. So this has applications in the management of energy grids and also applications of fire management. So that's really interesting to see.
And I think those folks who are from Western U.S. or Western Canada really are interested in the fire management.
Canada now.
Dana, you guys have also done some stuff in emergency response and optimization of, let's say, satellites and things like that. Could you talk a little bit about that work?
Yeah, I mean, really, it's our satellite EOS optimization. So when you think of satellites, we have thousands and thousands of satellites up ahead, and they're deciding on what they're going to cover in terms of capturing imagery and different types of imagery. So, for example, we talk about wildfires. If you want to redirect your imagery in your constellation toward the wildfires, we have the D-Wave. We ran it on D-Wave optimization hardware, but we have the algorithms and the product to optimize the satellite imagery collection capture. We won actually the European Space Agency prize for that, and we're in talks with ESA now. And then we also developed and just patented or patent pending for Planck hyperspectral, so we can now auto-label hyperspectral data, which has been previously, nobody's been able to do it. We created the machine learning vector to do it, and we've been testing it on various hardware. It's not really an annealing problem, but we tested it on IBM's hardware. They gave us 127 qubits, and in 1 second we could label one image with only like 2 to 20 reference points. And we did it on 19 qubits of that 127 qubits. Now, AI takes a really long time to do that, and it needs 1,000 reference points. So if you think that, again, we have thousands of satellites in space, and we're collecting, billions and billions of hyperspectral images, and only a fraction of them can really be used meaningfully because they cannot be labeled except manually or very slowly. So this is solving a major bottleneck, and we're going to continue testing it on other types of hardware, but we certainly have a lot of government interest in it from the US and Canada, actually. And we published these results on Planck hyperspectral in SPIE. This is the Photonic Society for Defense. I presented that paper. It's published. We have all of this, by the way, that I'm talking about. They're in IEEE papers, SPIE, or World Economic Forum.
Fantastic. Let's stay in space for a little bit. Rima, you've always talked about quantum in space, and I'd love to kind of share your thoughts with the audience.
Yeah, no, it's interesting when you learn more about the benefits of microgravity. It actually provides more bandwidth. It gives you more processing control, and it's possible that running a quantum computer might actually produce some different results in microgravity, and so it's worth exploring. And we do have some people now thinking about that. You think about noise, like Earth has gravitational waves that right. Earth is shaky. It's not stable. So it creates different types of noise. So you have more of a vacuum, and the only other thing you really need to worry about in space is radiation, which we've done a really good job of learning how to protect against that. So there's different ideas that are being proposed for how we could use sensing technology in space differently, and get different results. And we already have examples of that on the ISS. We're growing crystals in space. We're creating materials that could be used in quantum computing that will get different results. That we may actually dominate in creating new high-end semiconductors because we're growing these crystals in space, and that would make Taiwan look like second rate. How awesome is that for us to not have to worry about that? It's just, there's a lot of synergies in space for quantum, where quantum can protect a lot of assets in space, obviously through sensing and other things, and secure communications, but then also quantum could behave differently in space, so computers might give us different results. Wouldn't be shocked if fusion works better in space. I mean, technically the sun was born in space, right? So anyway, long way of saying that I think microgravity has a lot of different benefits for us that is worth exploring, and quantum will benefit either because we're bringing things from space for quantum or using quantum in space. So it's a whole nother market.
Well, I'm not going to say that we are getting a D-Wave space anytime soon. So we will go back down on the terrestrial plane. And Dana, you mentioned something very interesting, and I want to go to Andrew with this one. You mentioned, sorry, I'm bouncing around. This is what happens when I fill in for the moderator. You mentioned AI. And I know, Andrew, there's a lot of work that D-Wave is doing with the connection of quantum and AI and where that kind of inflection point comes. And I know quantum and AI are both buzzwords, but if you can figure out a way to easily explain like what is real in that quantum and AI intersection that you guys have worked on, and maybe demystify some of the hype.
There's a lot of hype in quantum, and there's a lot of hype in AI, and there's a lot of amazing work that's really exciting that's going on in both areas right now. I don't want to get too in-depth into the work that we're doing right now, but there's a lot of promising work with quantum annealing in particular and quantum computing in general in reservoir computing and diffusion and things like that. One main issue that is coming up with AI, which I think is a huge problem, is the energy consumption that is required. So I mean, there's nuclear reactors being commissioned for data centers now, and I mean, I don't know where this ends, but it might end with quantum computing to a certain extent, because we know that we can solve sampling problems not only faster, but enormously cheaper in terms of energy. And once you build that cryostat, which is kind of 25 kilowatts, you can put a lot of stuff in it, not just one chip. The scaling is very graceful in terms of the energy requirements that are needed and the throughput that you can get. And so I think that in terms of AI and quantum, energy efficiency is going to be a huge economic benefit that we hope to apply as soon as possible.
Great, thanks. Rima, over to you. Obviously, one of the remits of the Department of Energy is energy grid resilience security, and you've talked a little bit about the sandbox, but as Andrew mentioned, kind of the AI need is going to be there. What are you seeing from a government perspective that an industry should be able or could be able to help with, and what's keeping you up at night in that space?
I mean, I do think that, having access to energy is a great concern, right? Data centers and AI is definitely sucking the power out of the room. And as mentioned, we do think that quantum could help alleviate some of those energy concerns, right? So to the extent that we continue to build these hybrid quantum computers, quantum AI, quantum classical, the better we will be, because energy efficiency is going to be the name of the game, I think, going forward. So understanding how to streamline that information as much as possible, and where we can use quantum would be phenomenal. But energy security is definitely a concern, and we're looking to quantum to sort of bring us some relief potentially.
Thanks. Dana, obviously as a software company, you're not looking at the hardware, but you guys are building. You mentioned your ML work, and with Planck spelled with CK. I will remember that from now on. And you're working with AI. How are you guys seeing the intersection of quantum and AI?
So, I mean, I think the theme of many of these talks is that, this is how I would characterize it. We have enough quantum capability now to be using it and deploying it. And clearly, other countries are doing it. We're not doing that as much, and I would clone Rima and have 1,000 Rimas in government if I could get them. But our lawmakers are not quite they're not vibing with us on that. But as the hardware scales, we do have to bridge gaps with hybrid classical quantum solutions, and we're doing that very much. We'll use AI for pre and post processing because it doesn't make sense to deploy a quantum computer to do something that an AI computer could do quickly and cheaply and just as easily. We have to remember that quantum solves different levels of complexity different problems and different levels of complexity. So we have to make sure that we're deploying AI where it makes sense and deploying quantum where it makes sense. And what I think the nirvana would be is to have that continuum where they could be strung together or where they could be deployed in a way where you have the operation pretty seamlessly. So we're doing that now. So we have developed a lot of quantum algorithms alongside our classical algorithms, but we'll get there.
Fantastic. Andrew, over to you. Talking about other buzzwords, quantum and blockchain. Talk a little bit about that.
I thought it might be blockchain. Yeah. Blockchain. Yeah, blockchain is a big energy suck as well. There's this factoid about how much energy people spend on Bitcoin. And the country keeps on changing. It used to be Peru, now it's Sweden. Bitcoin mining is using more energy than Sweden. Which is pretty amazing. So this is another area where quantum can help and does help. So we put up a preprint on the archive in March or February of this year, demonstrating a distributed proof of quantum work blockchain with 4 different QPUs solving a problem for basically replacing the hashing function in Bitcoin with a quantum sampling function that is intractable for classical computers. So this is something that, will reduce the energy consumption to, I'm not saying that we're making a currency based on it, but if one did, it could knock the country down the list a little bit, because this is a big problem as well.
And for those of you who I haven't met yet, my foray into quantum was 5 years ago. Prior to that, I was fintech. And so seeing the intersection of quantum and blockchain kind of speaks to my history. So I appreciate kind of seeing how things are connecting together. And when I started with the company, that wasn't even an idea in anybody's head. And so it's the amazing advancements that the hardware and the software have been able to get to that allow us to do things today that we weren't thinking about even 24 months or 36 months ago. And with that, I'm going to go to Rima last on this question, but it is going to be a question for the whole panel, because I don't think you want to actually, well, I know you well enough, you probably would. What does the U.S. government have to do more of with regards to quantum? And then what are the areas, because governments in general need to do more with less resources, how do you see kind of quantum and emerging technologies helping? Because you can't stop public sector services. You have to still provide those.
I'm trying to think about how to not step on landmines here.
We can start with Dana. She can step on the landmines and then you can answer. There you go.
I'll throw the landmines, stamp on them. I would just back up and I would say, what is it that we want? I mean, I used to be in the government. I'm no longer in the government. I work alongside and help the government, so I'm an ally, but I have a little more freedom maybe to say some things that Rima does. But as someone who was in government and helped make, appropriations requests across large agencies in the many, many billions, and working with that process now, I think we have a little bit of an issue in that we say that we need to dominate these technologies and stand ahead of our nearest peer competitor, which is China. But I don't necessarily see us behaving that way from the congressional standpoint, and I'm sorry if there's anyone here from Congress or staff. We love you and we'll work with you. But honestly, like, the Quantum Initiative Act was never reauthorized. We don't have anything that is really propelling in legislation any kind of quantum application or small business or innovation. Right now we have hyperscalers going in and kind of dominating things, and we're wondering, like, where does that leave us as a small innovator with, we think, a superior product? And I mean, we look across the landscape and China outspends us 10-1 on tech and 4-1 on quantum as of 2023. And that's published in Boston Consulting Group. I'm not like pulling this out of thin air, right? And we all work in the business and we go to other countries and they're actually paying for this 30% ROI now, deploying quantum now, whether it's telecoms, the food industry, space operations. We have a client in the Gulf that is interested in deploying this for maritime stewardship through the government and through shipping and ESG stuff. And so they're willing to spend a lot of money. I mean, a lot of money. And, when I was last in the UAE, they not only funded $100 million into just a single solitary photonics lab, but then took that output and deployed it to detect COVID at the airport border point of entry. So they're not just like doing science projects for science projects' sake, they're actually deploying it. The Europeans are very active and deploying things, the Koreans, the Japanese, et cetera. So while other countries are out there like really leaning into quantum, I feel like we say we're leaning into it, but I don't see where in the legislation or the funding. Our funding is still very narrow, with the exception of, I think you're probably the only really applied lab, maybe? I don't know, sort of ish. The focus is hardware, PNT, cryptography, and sensing, and the rest of it is, and that's really not what the Chinese are doing. Xi has a 5-year plan, which he will release, and they are absolutely going for it to unseat us. And we are going to have a Sputnik moment in the next 1 to 3 years because we think we're ahead. And our government officials continue to go out at all the conferences saying quantum is 5 years away. What does that do to our investor community? What does that do to us in terms of competitiveness? That's super unhelpful, and it's also not true. So I think we have a lot to lean into when it comes to government. And I can say these things because I no longer work for the government. Anyway, so like I said, I would have 20 Rimas if I could.
So Rima, she's thrown out the landmines. Which ones do you want to walk around?
Look, I do think that we could do more if we had more, right? I mean, that goes without question. Phase 1 of DOE's investments in quantum went to basic science research, and we stood up these QIS centers, and they've done phenomenal work, and it was very hard to do, and they did it. Phase 2, I can say, my politicals gave me the green light to say, yes, we want to move now more towards the applied side. I'm hearing that from my political leadership. That's what they said. We want to figure out whether we can use SBIR money for quantum, applied quantum, and we don't want just phase 1, phase 2, we want phase 3. And so we're going to be figuring out how to do that. It's hard to do that until we get a budget. So we're waiting. But again, we are leaning in on more of the applied work because we do see a need for it, and we think that the energy sector is well positioned to be an end user and a customer. Look, that's kind of the bottom line. In terms of like what some of our neighbors are doing, yeah, they're outspending us, and that's not okay. And so we do need to mention that. We do have to talk about it because that's the reality we're accepting. And so do we want to accept that?
Well, we only have a few minutes left. I guess I'm going to ask each of the panelists. Andrew, I was not asking you about the U.S. government being a Canadian. I wanted to be mindful of that. I guess, this is now multiple years in from the National Quantum Initiative in the U.S. The Canadians had the National Quantum Strategy. There's quantum all over the place, all over the globe, working on this. This is, I think the 4th year of the Quantum World Congress. What do you wish the industry would do more to help you in your mission? Or what do you think we as a community need to start saying? Because I feel like sometimes we're not helping ourselves in this mission. And so, Andrew, let's start with the hardware side of it. What would you hope like the quantum industry would say, and maybe where we should go as an industry?
Well, I think everybody is forging their own path, and that's great. There's a lot of things being said that there's a range of technical advances and a range of claims being made, some of which are less easy to believe than others. And so having a little bit more concentration on the probability distribution would be nice, so that it doesn't turn people off of the progress that people are making in quantum science and technology. And as for support within the government, I think most quantum companies are doing pretty well this year. But it's always better to have more support. You can't win a space race without funding, and if we can get more users using the quantum processors and doing more things like materials simulation and design, then that's going to make things go faster, and we're just going to make progress. We're going to chop years off of the timelines, and so that's what I'd really like to see.
Fantastic. Dana, from the software perspective.
I think a lot of attention is on the hardware, and people are forgetting how are we going to compute this stuff. And what we try to do is work with the customers, of course, and what their needs are, but we also try to make it so that it doesn't need to be customized, because that's a heavy lift. But I think more collaboration in the industry. I see a lot of companies trying to dominate the entire value chain of the quantum compute spectrum, and it is maybe difficult to have a level competing playing field if I'm going up against AWS and they're sitting on all the contracts. That's not necessarily helpful. They're a great company, we love them, but I think there needs to be more competition, but there also needs to be more collaboration. So we have worked well with D-Wave since day one. We have a good relationship with IBM and with others. We're developing a relationship with IonQ and all the things. But I would say more collaboration. And then I think when you talk about getting real about the results, we are honest. We say, look, we cannot do 100% advantage, but that's okay, because why wouldn't you want to have 30 or 40% ROI, or reduce your expenses, or increase safety? We have FAA algorithms. Why wouldn't you want to increase your safety? There's a lot we can do. And I would just say, we need to have a better messaging around that. This is deployable now, but this is still in the pioneering phase. And that's okay. That's how we moved from a telephone, to what we have now.
And Rima, from a government perspective, what can we do to help you?
We need to better articulate the ROI, right? And also maybe even just articulate it in a way where it's not just quantified if we have a completely fault-tolerant quantum computer. It's phased. What is the ROI if we deal with and dominate on figuring out how to optimize what we have now? and then what's the next phase, and then what's the next phase. So that we show a path. We create a map forward that we can articulate, we can quantify, and then going back to Dana's point about collaboration, we need more of that. We need public-private partnerships. We need at DOE just got a foundation. Maybe we can leverage that somehow in the mix, especially to help with some of these collaborations and partnerships and create these convening opportunities. But we need to tell a better story about what the market size is, what the return on investment is, and talk about how we can actually bridge the gap between what we have today with tomorrow.
Thank you guys so much. We are at time, but as you heard, collaboration and working together in partnerships is important from the hardware, software, and government perspective. So please don't hesitate to reach out. And thank you all for being here.